All right, for those of you who are sitting back there, I'm sorry if the screen is not real bright. I suppose it's a chance for you to watch it again, at least on the video, if we're zooming in. Hopefully it's good enough. And once again, we're reminding you that we're trying to review things each time. We're trying to interleave different things. And again, according to this book, that's the best thing that we can do as far as your learning. Though I do feel like I have to talk fast a lot, it is important that you try your very best to have your mind turned on and you're listening to every word that I say, because it really is all important if you're going to understand statistics. Had another technological mishap with this classroom in that your head was in the way here. That's okay. Didn't mean to. This stuff I should have written up here so that we could see it with the camera, so I'll rewrite what's down there. Canceled the SX's and got R times SY, so you can go back to lecture A to hear what I had to say about that. That's the word that we missed with the video camera. All right, let's go back to the screen here. So again, you're going to be trying to make a graph like this one here on the left. You won't be trying to make a graph like the other one because we didn't have enough time to talk about it, but maybe next time we'll talk about that one. You should label your graph. I labeled mine based on my situation. Cumulative proportion of those who ate out last week. We're sampling from a population with p equal to 0.6. Trial number down there, proportion over there. What's your example that you'll be doing? You'll be doing simulated coin tossing and making a similar kind of graph for simulated coin tossing, coin flipping simulation. Trial number here. Here we're going to do this, the sample outcome is a 0 or 1. Think of 0 as representing tails and 1 representing heads. Okay? I'll say that again. Write it down if you need to. 0 represents getting tails, 1 represents getting heads. And so, if you use RANDBETWEEN, your low is 0 and your high is 1. So type it like that, RAND equals RANDBETWEEN 0, 1. That will always either produce a 0 or 1, evidently with equal probability, equal chance, of a 1/2 chance, 0.5 for each one. So you should expect about 50% heads and 50% tails, 50% ones and 50% zeros. For this first one, it produced a 1, so that's a heads. And you copy and paste down all the whole way. Wow, that's a bunch of 1s in a row. That can happen. Now it mixes it up. You can get a bunch of heads or tails in a row. That can happen. All right, you'll do the cumulative numbers. So actually, you don't need the COUNTIF for the first one here. You could just do equals C2 for the first cumulative thing. So I didn't have to use the equals COUNTIF for that first one. But for the second one, you should do equals COUNTIF. That cell, comma, you want to count it. Let's count it. We're counting the number of ones, is what the heading says. So we need, in quotes, we need to put equals 1, since we're trying to count the number of ones. And then we add, don't forget to do this, the previous cumulative amount, which is in cell D2. So that's the formula you want, such that if you copy and paste it downward, click and drag the lower right corner, it should keep track of the cumulative number of ones as you go. And you can confirm it's working with, look at these data here. Here we're getting 6 1s in a row. So these numbers keep adding up to 6 and before we get our first 0, which is a tail. And it stays at 6 until we get a 1 again, making it 7. And once again, you can also calculate the cumulative proportions, fractions, by taking the cumulative number and dividing by the trial number, which again is in B, column B. And it's ultimately those proportions that you'll graph by clicking on the trial number column, doing a control or a Mac, I guess you got a left click and Alt or something like that. Highlight both of those, go to Insert, Chart. Don't pick the one it gives you there. Pick a different chart type, pick a line. and also click this bottom box here. Okay? So here's what my graph looks like initially. Where's my slider here? I don't see my slider. Here's what my graph looks like initially. And you should expect the graph to get closer and closer to 0.5 overall, because that's your chance of getting heads on any flip, on any simulated flip. Okay? Everybody, by the way, should get different graphs. No two graphs should look the same. But they should still have similar properties in approaching 0.5. And again, you'll go do it for all these trials, which I believe is 100 of them again. Yes, I go down to 100 there. Okay? That'll be your electronic assignment for next time. All right, in our remaining time, we're going to talk about probability and how it's related to, for example, coin flipping and other things. What is a probability? A probability is a number we assign to an event in a random environment or in a random experiment to assess the chance or likelihood of the event. In essence, it's a measure of how certain we are that an event will occur. And I got a typo there. It should be the event right there. I guess I can change my typo right away now. Escape event. All right? At the extremes, if the probability is 0, then you're certain the event's not going to occur. What's an example of an event with probability 0? I feel like saying it won't snow tomorrow with probability, or it will snow tomorrow with probability 0, meaning it won't snow tomorrow. Though in Minnesota, you can never be sure, even in September. Let's see. I feel confident in assessing with probability 0 that I will be on the moon tomorrow. Okay? Meaning I won't be on the moon tomorrow, guaranteed. Probability of me being on the moon tomorrow is 0. On the other side, probability of 1 or 100%, you're certain it's going to happen. And again, we can't really be certain about anything, but it seems reasonable to assess. My probability of staying alive for the next second will be 1,001. Okay, I did. I made it. All right? There will be some second in my life where that won't work. A long time from now, hopefully. All right, so probabilities are numbers between 0 and 1, or as percents between 0% and 100%. Ideally, this number reflects proportion of times an outcome would occur in a very long series of repetitions. Now, we don't always do it that way. It's not always a random experiment where it's a repeatable environment like coin flipping. For example, meteorologists are trying to assess the probability of rain tomorrow. They might guess 0.2 or 0.3 or 0.4. They could be wrong. It's not really a repeatable environment, so it's not the best use of probability ideas. But ideally, you try to do it in a very long series of repetitions in repeatable environments, random environments, where the conditions are the same. That's the best situation to do it in. When I flip a coin vigorously, the most logical estimate of the probability of getting heads is 0.5 or 50%. 1/2. Is this estimate exactly right? How would I know? Got a coin. Flipped it. It's tails. Okay. It keep changing the way tails looks. Okay. It is tails. It's not an eagle anymore. What is that? I can't even tell. Ah, I can't tell what it is. What is tails? It's not a fish. I don't know what it is. Heads looks the same. Okay. Isn't exactly 0.5. I'd have to experiment over and over and over again. How many times? Thousands, millions, forever? When we're in heaven for all eternity, should I flip a coin every day, quote unquote? And see what happens? Will it ever equal 0.5 exactly? Well, it sometimes will equal 0.5. But usually it probably won't be exactly 0.5. And how do I know the probability is exactly 0.5? Well, I actually don't. It's actually not likely to be exactly 0.5. Pun intended. Okay, it could very well be 0.4999999999999. Stop. Or it could depend on how vigorously you spin it. But you know, it really doesn't matter much for most situations. As long as it's reasonably accurate as a model, it fits the data well, it's not a real big deal whether it's exactly 0.5 or not. it's a reasonable or logical thing to assign to a coin flip. I am going to move on. If you're writing notes, you can get the PowerPoint after class. I will try to put it up sooner. I didn't put it up right away last time. But is coin tossing really random? Actually, the mathemagician, and that is an official word, mathemagician, Persi Diaconis, can make a coin come up heads every time. And it looks like he's flipping it vigorously. He knows exactly how to spin it and how to catch it to make it come up heads every time. You can click on this link to watch him do that. It's about a 3-minute video. I would do it in class, but we're low on time. And also I found out that if you even show little video clips in class and you're videotaping and you're putting it on YouTube, YouTube's bots find your video and tag it as a copyright thing. So I'm not going to do that. But you can go there and watch him do that. It's about a 3-minute thing. He does more than the coin flipping. He talks about randomness, and it's worth listening to his ideas about randomness. Again, you'll simulate coin flipping. That's what this slide emphasizes. You'll create a toss series graph. Here's an example of a toss series graph I got from the books website. A couple toss series graphs. The number of tosses scale is logarithmic here. You don't have to worry about what that means. But do notice in the limit, essentially, these graphs are both approaching 0.5. They're both approaching the theoretical probability in terms of it's really like a sample proportion of times that you get heads. That p hat, if you will, keeps approaching p, though there are ups and downs. What is a probability model? Important idea. Some terms here. The sample space of a random phenomenon is the sum of all possible outcomes. The letter S will often be used to denote the sample space. An event is a particular outcome or set of outcomes in a random phenomenon. The event is a subset of the sample space. A probability model is a mathematical description of a random phenomenon. It consists of 2 parts, describing what the sample space is and a way of assigning probabilities to events. Here's an example. Toss a coin 3 times and count the number of heads. So when you do that, you're going to get 4 possible outcomes: 0 heads, 1 head, 2 heads, or 3 heads. 4 possible outcomes. What probability should I assign to those outcomes? The sample space is 0, 1, 2, or 3. How do you assign probabilities to those different x values? I can make a little table. This is not real precise notation, but don't worry about it. 0, 1, 2, or 3 are the different possibilities for the number of heads. Without explaining it, I'm going to assign probabilities of 1/8 for getting 0 heads. Bring this in my head here. Pun intended. 3/8 for 1 head. 3/8 for 2 heads, and 1/8 for getting 3 heads. If you wanted to explain this, what you could do is you could write down all the different HT combinations in 3 trials, HHH for example, HHT, etc. And you would see that 3 out of the 8 have 1 head, 3 out of the 8 have 2, 1 out of the 8 have 0, and 1 out of the 8 have 3. Okay? I would encourage you to do that, in fact, it's not too hard. I'm assuming each of those possibilities is equally likely as well when I write these numbers down. This is an example then of a probability model for a given random experiment. Do notice these probabilities are never negative. Probabilities can't be negative. And they add up to 1. When you add up these fractions, you get 8/8 by adding the numerators, and that equals 1. That's a couple important properties about probability models as well. Okay, fairly simple example. Again, I would encourage you to write out the list of possibilities again to see why that is a good model. Some models are legitimate, some are illegitimate. Look at this situation. The random experiment we're thinking about is rolling 1 die, 1 6-sided die. There are 6 possible outcomes. 1, 2, 3, 4, 5, or 6 is what shows on the top of the die. Which of these models is legitimate, which is illegitimate, which is best, which is worst? Are any of them really good? Doesn't look like any of them are good. Which are legitimate and which are not? Well, first of all, these probabilities are all greater than or equal to 0, so they actually, in that sense, are legitimate. However, none of them are negative. However, they don't all add up to 1. For example, this column, this model, the numbers don't add up to 1, so that's illegitimate. You can't use such a thing as a probability model. These numbers don't add up to 1 either. They add up to 6/7. That's illegitimate. Let's see. This model doesn't add up to 1 either. That adds up to what? 7/6? Illegitimate. This model is legitimate. All these numbers are greater than or equal to 0, and they all add up to 1. Does that mean it's accurate? I guess that's not a question here. No, okay? I don't think the probability of getting a 4 is 0. That's not a good assignment of a probability. The best assignment, the most logical, would be 1, 6, 1, 6, 1, 6, 1, 6, 1, 6, 1, 6. Have them all have an equally likely chance of happening. That would be the most logical kind of model when you're vigorously rolling dice. Assuming there's no magnets inside the dice and no magnets inside the table. Assuming ordinary kinds of situations where you're vigorously rolling. So to be legitimate means the numbers have to be greater than or equal to 0 and all add up to 1. And it's illegitimate otherwise. But if it is legitimate, it doesn't mean it's a good model. It doesn't mean it's accurate. It's a reflection of reality. Here's more dice probabilities. You can imagine rolling 2 dice. There's 36 possibilities because there's 6 possibilities for the first die and 6 possibilities for the second. And when you do think about the situation, you should think of one die as being the first die and the second one as being the second. Maybe it's good to think about them as being colored. One is colored red, one's colored green or something. It's good to think about the model in this way so that there's 36 possibilities. What's the probability when I roll 2 dice that I'm going to get a sum that's even? Turns out to be 1/2. If you assume each of these 36 possibilities is equally likely, then any one of them has a 1/36 chance of happening. And how many of them are an even sum? Well, 6 plus 6 is 12, which is even. 6 plus 4, 5 plus 5, 4 plus 6, those are all 10, which are even. 6 plus 2 is 8, 5 plus 3 is 8, 4 plus 4 is 8, 3 plus 5 is 8, 2 plus 6 is 8. Those sum to the even number 8. Where am I? Coming back down here. 5 plus 1 is 6, 4 plus 2 is 6, etc. Going up these diagonals. 3 plus 1 is 4, 2 plus 2 is 4, 1 plus 3 is 4, and then 1 plus 1 is 2. I focused on all the die combinations whose sum is even. Turns out there's 18 of them if you count, and 18 out of 36 is 1/2. So you really do need to look at the picture and think about that to make sure of that. Okay, die, and you got 2 dice, it can be more complicated than you might think. You need to think about this full picture. How about getting doubles? 6 and 6, 5 and 5, 4 and 4, 3 and 3, 2 and 2, 1 and 1. Those are the doubles. There's 6 out of 36 of them, or 1/6 is the probability of getting doubles. By the way, this is probability notation. When you see the P here in this chapter, it stands for probability. What's the probability of getting doubles? That's how you should read this. Okay? This entire symbol represents that number. Probability of getting doubles is 1/6. What's the probability of not getting doubles? It's the opposite of this number with respect to subtracting 1. 30 out of the 36 are not doubles. That's a 5/6 chance. These two numbers, because these two events are complementary, must add to 1. You can find this number by doing 1 minus this number. To a sum less than 6 means 5 or less. That would include everything along this diagonal and below. How many are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 possibilities where the sum is less than 6, which is the same as the sum being less than or equal to 5. 1036, which does reduce as well to 5/18. I didn't bother reducing it, but that could be reduced as well. So again, the dice combinations there essentially are your sample space, and we can assign probabilities to different events based on counting. When you've got a finite sample space, which is what I've been talking about, you assign a probability to each individual outcome between 0 and 1, and a sum must equal 1. The probability of any event is the sum of the probabilities that make up the event. For example, the event that you get less than or equal to 5 can be thought of as being made up of the event that you get equal to 2 for the sum, equal to 3 for the sum, equal to 4 for the sum, or equal to 5 for the sum. Those are different events, and the entire probability of getting less than or equal to 5 can be thought of as adding up the probabilities of each one individually. Now I'm going fast because we're low on time. You can have infinite sample spaces too, intervals of outcomes. How do you assign probabilities for those? With areas under density curves, just like in chapter 1. For example, if you have a situation where you've got a random experiment, you're measuring something, X represents the outcome, and if a uniform distribution like this is a good model for the values of X all between 0 and 1, the area of that rectangle in this case would give you the probability that X is between 0.3 and 0.7. What's the area? Well, it's a rectangle, so the base is 0.7 minus 0.3 is 0.4. The height is 1. The area is 0.4 times 1, which is 0.4. A probability that X is less than or equal to 0.5 or greater than 0.8. Add up these two areas. It doesn't matter really with continuous ones like this, whether you use less than or equal to or less than versus greater than or equal to or greater than. I didn't say that quite right. Less than or equal to versus less than, or greater than or equal to versus greater than. Those boundary values really don't matter so much. You focus on the areas just like we did in chapter 1. You can do this with normal curves as well, or triangular distributions, making sure in any situation where you're using a density curve to model probabilities that the total area under the curve is 1. That's analogous to probabilities adding to 1. And again, the area is the answer. If you want to got a situation like this, the area of that is going to be the probability that Z is between 1.4 and 2.2. Hang with me here for another minute or two. We're going a little over time. 4 continuous probability distributions. It's the area. Warning, in this kind of continuous situation, the probability of the variable equaling something exactly is essentially 0 because there's no area of a line. A line doesn't have an area. 40,000 right there. What's the area of that line? It's 0. Lines don't have area. So you're always talking about intervals of numbers and finding areas under the curve for intervals of numbers. 2 terms. When X, the variable you're measuring, is like a whole number and can only be a whole number, for example, it's called a discrete random variable. For example, the number of heads in 3 tosses can either be 0, 1, 2, or 3. That's called discrete. On the flip side, when a variable can take on a range of values, any number in a range of values, like a time interval, or a measurement of a height, or a volume, those are called continuous random variables. They take on values along a continuum. You use the discrete models with the tables for discrete random variables. You use density curves to measure probabilities for continuous ones. All right, see you next time.